Hello everyone and welcome to today's webinar. Today's webinar is titled Biomechanical Investigation of a Passive Upper Extremity Exoskeleton for Manual Material Handling, a Computational Parameter Study. My name is Christopher Iversen and I work here at Anybody Technology. Today I will be the host of this webinar and I'll be joined by my colleague Bjørn Kjær Enhed, who is also a research and development engineer here at Anybody Technology. Bjørn will be joining us during the Q&A session and help out with answering the questions. Today we have an external speaker who is Bo Eidel Seiferheld, and Bo has a master degree in sports technology from the Department of Health Science and Technology at Aalborg University here in Denmark. And he's going to give his presentation in a minute or so. But just before we start, I will give you a general introduction and overview of the Anybody modeling system for those of you who is unfamiliar with the software or musculoskeletal modeling in general. So, what is the Anybody modeling system? The Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates internal body loads as joint moments, joint reaction forces, and muscle forces. And here in the bottom of the screen, you can see a screenshot from the Anybody modeling software, which can give you an idea of how the system actually looks. At the moment, Anybody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, and assistive devices as exoskeletons, which we are going to learn more about today. The typical workflow in Anybody could look something like this. You provide the recorded motion data as input and use the body models which you or others have built. And then you provide some kind of environment, which, for example, could be an exoskeleton. Then you can use Anybody to combine these things and solve the muscle recruitment and then run the inverse dynamics simulation, which basically means that we go from motion to calculate the internal body loads and the interaction with the environment in some cases. The actual simulation looks something like this. You can then output the results and use it for some post-processing, which, for example, could be with some kind of finite element tool. But many users also closes the loop completely by doing some kind of design optimization and then run this cycle multiple times. I think this brings me to the end of the introduction, and I will hand over the word and presenter role to Bo instead.
All right, thank you. Thank you very much, Christopher, for the introduction and for inviting me today for this webinar. And first of all, a warm welcome to everybody at home listening in for today's webcast. As Christopher mentioned, I will be talking about a project we did entitled a biomechanical investigation of a passive upper extremity exoskeleton for manual material handling as a computational parameter study. This study was part of our collaborative study with Aalborg University and the National Research Center for the Working Environment. So let's get into it. We know that there is a strong evidence for the association between work-related musculoskeletal disorders and manual material handling tasks. And we know that this is especially due to highly repetitive motions and people working at awkward working postures and high forces when exerting this motion. And this is very prevalent in the supermarket sector, and approximately 40% of all the grocery workers suffer from either shoulder and or lower back disorders and pain. So how can we help these workers? Well, one of the new tools on the market is ergonomic exoskeletons. And in this case, we're talking about upper passive extremity exoskeletons. And I've brought a picture here of a lot of different exoskeletons just to give you an idea of what they could look like. An exoskeleton is basically a variable mechanical structure that enhances the physical capacity of a person and are usually categorized into either being passive or active. In this case, we're talking about the passive exoskeletons, which comprise a spring or counterweight designed to aid different body joints by storing and releasing energy. And this could be an example here. So you have a spring here in the arm mechanism, and then you transfer the load down through the frame onto the hip joint. This is basically the concept. So how is it all related? Well, there is a lot of different studies out there in the literature, and very often the results show that you can find reduced shoulder flexor muscle activity and increased endurance for a lot of different exoskeletons. Some of the exoskeletons also find reduced spinal loadings and increased productivity when using the device. And this is just a brief introduction to some of the studies out there. Others, however, on the other side, we have some consequences that we have to be aware of. For instance, we see altered kinematics. So when people are performing a task with an exoskeleton, we can actually detect change in the motion and the way of performing the task. And we also see additional muscle activity being recruited, which is usually at the erector spinae muscles and the internal obliques from the extra mass that you are carrying when you're carrying the device. Some studies also indicate that we can have increased spinal loadings in some cases. And when we are performing some more fine motor skills, there might be some more errors apparently in some of the studies. So the issue with the exoskeletons is that they're very conflicting in terms of beneficial effects, and this is most likely due to the different designs. As you can see, there are a lot of different ways to go around this issue. But one way we can actually address this issue is by using musculoskeletal models, because then we can simulate a variety of interactions with an exoskeleton. And that was also the motivation for what we did in this study. We wanted to take out a specific exoskeleton and try to look in depth of how we can understand the interaction for the exoskeleton and the human body. So basically, we wanted to design a method to evaluate the biomechanical risk factors associated with using an exoskeleton. And we did this based on inertial motion capture data of manual material handling tasks that we performed in 2 different supermarket stores. Before I go into depth in the experimental procedure, I would like to say that this study was part of a larger project where we aimed at determining the biomechanical loads, muscular demands, and working postures doing different manual material handling tasks in the Danish supermarket sector. And if you want to know a bit more about all of the other tasks that were analyzed and captured, you can go check out a previous webcast by Sebastian Scals, who's also a co-author for this paper, or you can see his journal paper here for the part 1 of this work he did. But I just noticed that there is a new paper that came out yesterday, which is the part 2. So you can also go check that one out. It's not linked in the references later, but you can still go check it out if you want. All right. So I have a picture of the exoskeleton that we used for our project. So this is the shoulder exoskeleton from Sudex. And we have the exoskeleton over here with all the cushioning and padding and so on. And here at the middle, we have the CAD model of the exoskeleton that we created. And of course, a nice little figure here to let you kind of get an idea of how it looked like when you're turning it around. So I would like to talk to you about how the exoskeleton works. So you can adjust the arm length from 1 to 7. And you can adjust the width of the shoulders and as well as the torso height. And then it, of course, has some sort of locking mechanism that you can use to lock the exoskeleton in place when you're not using it. And then, of course, you have the arm brace and an on and off switch. But most importantly for what we did is this mechanism of peak torque amplitude and torque amplitude indication. And I'll talk to you a little bit more about that. So you can adjust the torque output from a setting from 1 to 5. When you're turning this knob, you're providing a bigger torque or lower torque, it depending on what way you're turning it. And then there is this red dot that indicates at what setting you are performing the task right now. And then there's another setting, which is the support angle that goes from 60 degrees to 120 degrees. And let's go a bit more into what happened. So, or what actually happens. So if you are peaking, or if you're choosing the setting that 90 degrees, you're peaking the torque at a 90-degree angle flexion, but you're engaging at 20 degrees and disengaging the device at 130 degrees. The actual torques that we used, I cannot share with you in this presentation today, but it will be available later this year and in the paper when it's hopefully getting published. So what we did then was that we recreated this torque profile in Python and implemented it into Anybody so that we could provide a torque that was engaging at 20 degrees and disengaging at 130. For this particular example, with a torque amplitude, this could, I don't know if this is 2 or 3, but what it is, but this could be one of the profiles. Then we would regulate the torque amplitude by turning the knob or changing the peak, changing the torque that we provide the upper arm. And then we could also change when to provide this torque. So we could skew this either down towards the lower degrees of flexions or higher degrees of flexion. And you can also find additional information out here on number 19 if you want. So let's go into the experimental procedures. So here's what happened. We had 15 full-time employees at 2 different supermarket stores that were performing a 2-handed lifting task of 7.9 kilogram rye bread. As you can see here, they had a starting position of 15 centimeters above the ground, and then they ended the motion when they placed these rye bread cases on top of the shelf at approximately 145.5 centimeters above the ground. And while they were performing this task, as you might have noticed, they were equipped with the Xsense Avinda system, sampling at 60 Hertz, and they were recording full body kinematics. Then we implemented or imported this full body kinematics into the Anybody modeling system using the BB8 Xsense template. And this stick figure model here is from the Xsense, and then we have the stick figure model for the Anybody modeling system. And the issue with these 2 models is that the stick figure model for the Xsense has 72 degrees of freedom, while the Anybody modeling model has 44 degrees of freedom. So what we did was that we performed a virtual marker tracking method. So we placed markers on both the stick figure model and the musculoskeletal model, and then we solved this, solved it by finding the least square difference between these 2 markers between the models, and then we had the musculoskeletal model kinematics. Then we had a box model that we created in the SolidWorks and the exoskeleton model that we also created in the SolidWorks software. The box was according to the measured geometry and weight that we were measuring during the initial capturing of the data. And the exoskeleton was created where we had some CAD model provided by Sudex, so that thanks for helping us with that one. And then when we were implementing these into the Anybody modeling system, we always changed the settings, for instance, for the torso height and shoulder width, so that it accommodated the musculoskeletal model according to the fitting guide that was provided by the Sudex guys. Then we had to capture the kinematics of the box and the exoskeletons, because this was not captured. This was only data. We only used data from the full body kinematics. So what we did was that we placed a point in the middle of the hand and on the handle of the box to solve the kinematics of the box, which was again with the same method as previously with the virtual tracker method. And we actually did the same for the exoskeleton. However, we had some nodes on the hip brace and the lower back, as well as on top of the exoskeleton here at the width adjustment and on the just above the elbow joint and on the arm brace. And then we solved the kinematics again to get the kinematics of the exoskeleton. Then we went on to perform our inverse dynamics analysis. And over here we have the analysis without an exoskeleton, and we used a method for predicting ground reaction forces. And basically this method utilizes 25 dynamic contact elements, which is distributed here underneath each foot of the musculoskeletal model, and each of these dynamic contact elements has 5 uniaxial force actuators, which can generate a normal friction for a normal force, alongside positive and negative static friction forces in the anterior, posterior, and mediolateral direction. And then we actually performed the analysis, of course. We also predicted the reaction forces for the interaction with the hand and the box by implementing these contact elements here as well. And then we had that analysis. That was just one of the simulations we did for the 15 subjects for all the 4 tasks or the 4 repetitions that they performed. And then we had this whole parameter variation where we, for instance, had one torque profile with a specific angle setting, perform the analysis, change the settings to another, maybe increase the torque, but with the same angle amplitude, the same angle, and then we perform the analysis again. And also here we use these contact elements to predict the reaction forces that occurred with the interaction between the upper arm and the exoskeleton arm brace, as well as the hip here, the hip brace here. So if you want to know, can I please not, okay, I cannot change slide, there we go. If you want to know more about some of the methods that we used, you can check some of these references that I have put down here for the virtual market tracking and the least square difference method, and as well as the ground reaction force and moment prediction method. So here is a little slide with 3 video recordings or animations of what it would look like. So we had the person performing the actual manual material handling task at the supermarket store, and then we had the kinematic analysis as well as the inverse dynamics analysis over here. So to sum it up, we had 27 different settings that we simulated. We had the 5x5 exoskeleton settings ranging from 1 to 5 in the torque output and from 60 to 120 in the torque angle. And then we also had a setting where we had the exoskeleton on, but we were performing it without support. And then we had this no exoskeleton setting where we performed the task without an exoskeleton. We extracted a lot of joint reaction forces in the lower lumbar region of the spine, as well as glenohumeral joint reaction forces, and a lot of different muscle forces. And we normalized all the data to impulse and peak forces as a percentage of the body weight for each person. So here is one of the graphs and how it would look like, and I'll like to take you through the graph so that you get an idea of what's going on. So on the vertical axis here, we have the L4, L5 compression force normalized in terms of impulse. And then down here we have the SL, which stands for the support level, which goes from no, which means we're performing the task without an exoskeleton, to the setting 0, which means we're performing the task with an exoskeleton, but it's not activated torque, and then the range from 1 to 5 in terms of torque amplitude here. And then on the other axis, we have the support angle SA here, which refers to the different support peak support angles. So if we have 90 degrees, the torque output is peaking at 90, engaging at 20, and disengaging again at 120 degrees. So that we have here, we have the L4, L5 compression and anterior posterior shear forces. So when we look at the data, we could see that when we were increasing the load to the musculoskeletal model when we were performing the task with an exoskeleton but without support. And this of course makes sense because we're adding more mass to the system. So of course there will be more compression force in the lower spine. And then when we were looking at how the interplay was with the regulation of the settings, we could see that there was usually a linear indication of increasing the torque output. So when we were increasing the torque, we were also decreasing the compression in a linear manner. However, when we were regulating the peak support angle, you can see that it had a more non-linear like behavior. And when that meant when we were choosing a setting that was inappropriate in the angle, but appropriate in the maximum torque, we did not see that big of an impact from the exoskeleton. And also the opposite when we were choosing a correct angle, but an incorrect torque output or low torque output, it was also not that great. So the best setting was usually at 90, with it peaking at 90 degrees with maximum torque. When we were looking at we tried to compare our results a bit with the recommendation, which is 3,400 newtons for compression and 700 for shear forces. And we tried to compare it to the average subject that we had in our study. And we could see that without an exoskeleton, we were below these limits, which of course was expected, because lifting a 7.9 kilogram box should not be above the limits. And then we could see that when we are using an upper extremity exoskeleton, which is usually for the shoulder complex, we could actually also reduce some of the loading in the spinal, which is of course a great accomplishment for an upper extremity exoskeleton. However, as I was talking about in the introduction, I told you that some of these exoskeletons had shown increased endurance and productivity. So it expands beyond worker safety and well-being, because if you have a worker who's working without an exoskeleton, he might produce a specific amount of work a day, but when he is performing the task with an exoskeleton, he could actually improve his capacity. And if that's the case, we might actually end up in a case where he's working more at a working day, but the cumulative load over a day is the same, because the beneficial effect might cancel out, because we will have too much, we will be completing too many tasks. So we need to be aware of the fact that we are just not increasing the amount of work and still remaining equal in terms of load over a working day. And this is a general issue with exoskeletons in general and increasing the productivity. So here we have some of our results for the glenohumeral joint. We have the glenohumeral contact forces over here, and then we have the ratio where we took the ratio of compression compared to the anterior posterior shear force, as well as a yeah, that's pretty much it. So let's talk a little bit about what we see when we look at the glenohumeral joint reaction forces. We see that when we are performing the task without an exoskeleton, it's around 209% body weight in peak forces. But when we're performing it with the worst setting, we're actually increasing the peak forces quite a lot for the glenohumeral joint. And we also have indications where we reduce the loading for the resultant forces in the glenohumeral joint. And we try to compare some of our results, and we could see that this is 2 to 3 times what you would expect doing daily activities, which suggests that we have a very demanding task. And we also compared it to some other studies who had a 5 kilogram box lifted to shoulder height, as well as a 10 kilogram suitcase moved laterally. And as you might have noticed, all of the results indicate that at 60 with maximum torque, we are experiencing the highest reaction forces in the glenohumeral joint. And why is this happening? Well, an explanation to why this is happening is that we might actually increase or provide more torque to the human body that he needs for the specific time the motion is being performed. So in that case, the musculoskeletal model in the inner body modeling system would act against the motion, because it's not supposed to move the arm more up, it's supposed to keep them in place. And this will also be the case when we'll be looking at some of the extensor muscles that I'll present to you in a very short time. So yes, very high glenohumeral forces. Need to look more into this. So we know that the resultant force might lead to some loss in information, because the ratio helps us to try to predict the risk of injuries. And if we reduce the compression force, but we increase the shear forces, it might be indicative of instability. And this is because the compression force keeps the humeral head within the glenoid socket. So if we have an increased shear force, then it would contribute to a destabilization by translating the humeral head towards the glenoid rim. And when we were looking at our data, we could actually see that we were reducing this ratio in some sense when we are using the exoskeleton, which might indicate that we can get a more stable glenohumeral joint when we are performing the task with an exoskeleton. So let's look a bit into some of the muscle forces. We have the anterior deltoid here, the middle deltoid, upper trapezius, posterior deltoid, latissimus dorsi, and teres major. And as you can see, we see some of the same patterns in terms of linear reduction with torque and nonlinear with angle settings. And we also see this little thing I was talking to you about previously with the increased flexor muscle activity, extensor muscle activity at the low angle setting with the highest torque output. And when we were looking at our results, we could again see what I was talking about. Increased torque at appropriate angle would reduce the demand on the flexor muscle activity, but not on the extensor muscle activity or muscle force. And we try to compare it to the literature, but it's usually the peak and mean muscle activity, which is measured with the EMG systems. But we also find reduction in the forces up to 45%. And compared it with a previous study who used the shoulder X device as we did, and other literature using the Levitate airframe exoskeleton. So the consequence, of course, as I was talking about, was that when we provide more torque than we need for the motion, we are increasing some of the extensor muscle activity. And in some cases, we're also increasing some of the flexor muscle activity or muscle force, sorry. So as with any studies, there are some limitations, and I will, of course, like to adjust some of them. Of course, every time we use IMU-based motion capture data systems, there is some measurement errors compared to optical motion captures, but the XSense software has showed very satisfying agreement between optical motion capture systems and their own system. But there is, of course, some error present in that sense. Then we have the virtual marker tracking errors. So every time we, for instance, had to compromise the motion from the XN stick figure model to the antibody modeling system model, then we had to compromise the motion into one. So there will be some errors in terms of this virtual marker tracking method. Also, the box and exoskeleton kinematics were not measured in our study. It was directly predicted using these virtual marker tracking. And this, of course, has a limitation because you might expect the box to move in a certain way when you're performing the modeling, but in reality, it might change a bit more than you expected in the modeling, as well as with the exoskeleton kinematics. And this is a crucial part because some of the previous studies have shown that when we're using exoskeletons, we are actually changing the way we're performing the task. So in this study, they used the exoskeleton, and they showed that when they were performing the task with an exoskeleton, we had more shoulder abduction. So in our case, you might expect some change in the kinematic as well when you're using the shoulder X device. However, when we wanted to perform this parameter variation, it was not feasible to have a subject perform 4 lifting tasks with an exoskeleton at 25 different settings. So we did not do that. And we also wanted to kind of make a method that was feasible to go out to the factory with just a simple IMU-based system and then perform the analysis at home. And of course, there is also the whole subject about the correct modeling of the contact elements with the human box and human exoskeleton interaction. And we, of course, had some assumptions that we had to make here. And there is, of course, always room for improvement on this part. However, the idea was to create a model that could be feasible to have directly at the factory. So we did not want to have extra equipment in terms of force platforms and so on. So let's sum it up here. So we found that spinal and shoulder joints loads were reduced with the shoulder exoskeleton. we saw that the muscle force were reduced for agonist muscles. We saw an additional antagonist muscle forces in some of the muscles, especially latissimus dorsi and teres major. And we saw that the optimal exoskeleton setting was quite crucial, because if we did not choose a correct setting, we might actually lose this beneficial effect of the device. So this is something you need to be very aware of when you're using exoskeletons for alleviation of strains for your workers. And then lastly, we demonstrated that when we're using musculoskeletal, we can use musculoskeletal models in tandem with on-site kinematic data. And before I close the presentation, I would like to give a brief introduction to a Danish company called Agota. And what we do is that we are a brand new startup company with a burning passion to improve working conditions and prevent musculoskeletal disorders and pain. And what we do is that we perform these ergonomic risk assessments, where we use the newest research, which is some of it is what I presented to you today, to understand why a given working task is problematic, how the load risks are and injury occurrence, as well as how we can alleviate strain to retain the worker for the specific task. If you want, you can follow us on LinkedIn at Agota, or you can send, if you want to get in contact directly with the company, you can send a mail to info@agota.dk. With that being said, I have included all the references here for you guys. So if there was any of the papers or anything you wanted to look at yourself when you get the presentation available, you can always find it here in the reference list. And with that being said, I would like to say thank you for listening in. And here is an email address if you want to get in contact with me personally. And thank you very much for your time. And I hope that you all stay safe during this Corona time. Thank you.
Thank you very much for the presentation, Bo. I think it was very interesting. And so if you want to know more about Anybody technology, you can go and check out our website at anybodytech.com. And here you can find special events and other dates, for example, for webcasts similar to this one. We have also a full publication list there, which includes all of the studies using the Anybody modeling system. You can also go and check out our website anyscript.org, which is our community website for people using Anybody. And here you can find multiple online resources as our wiki page, several blog posts, and links to our repository sites. It's also here you will find our forum, where you can go and ask questions and get help from some fellow Anybody users. And last but not least, if you have any questions or you want to meet up or are interested in getting a trial version of the software, then please feel free to send us an email at sales@anybodytech.com or send an email directly to me at ki@anybodytech.com.